So today's workshop is on tips and tricks for collecting good NMR data. Um, so we are you by NMR core. This is me, Deb, Minley. You guys know both of us. Emily and Anne are part of the administration portion, as well as Emily is the faculty director. If you want to get in touch with us, our emails are here, our phone numbers are there. So that's how you can get in touch with us. Okay. So here are a few links to previous BioNMR workshop topics. These are already on our website. So if you go to bionmrco.umich.edu, you should be able to find these workshops. Even if you missed it, we record it and then we can like play it anytime that you want, or you can go back and look at it. And So in today's workshop is being recorded as well. So we'll share it in the website in a few weeks. And webcams are optional for both hosts and participants. And if you want to come on the stage and talk or ask questions, that's fine too. Please use that. And try to use the Q&A feature here on Zoom, and then that way you can ask questions. So today's topic is tricks and tricks for collecting good NMR data. So here I'm not going to say anything new. There could be a few things that are new, but it's more of like things that you have probably heard from various sources, or you have seen a few talks that give you certain bits of information could be useful. But this is kind of putting everything together into like one place, and kind of like things that you probably are doing it this way. If not, then yeah, please use this as a resource. What I will do with this is actually even create a PDF and put it right next to every spectrometer, so you can refer back to this if this is something that you're interested in. Okay, so there could be some slides that are redundant that you probably know. So this is not like trying to educate everyone. This is kind of like trying to refresh our knowledge, as well as kind of like bringing all the knowledge together in one place. Okay. So overall, so we're going to talk about. Let me minimize my video. Okay. Okay. So let's. So there'll be like 5 different sections of this talk. First, we'll talk about how to make good samples for collecting good NMR data. Then we'll talk about what parameters in terms of the instrument parameters that you can change. So these are something that you kind of overlook because of automation. But if you were to ever do it manually, or if you don't get good data in automation, you want to come back to the slides and do these things that I'm going to suggest. Then we'll talk about what does each acquisition parameter that you collect data in, what does that even mean, or like what should be a good starting point, or what is happening, or why you're seeing some things that you usually see and you know why. So we're going to go over that, and then we'll talk about how to do some efficient data collection strategies, very similar to the section in our third workshop. And also we will also give you some list of experiments that are the choosing the right experiments to do the correct to give you the correct data. Okay, so this is your overview. So let's go to the first where am I? Okay, so we are here. Let's go for good sample practices. So my recommendation is always use a good deuterated NMR solvent. You can buy solvents from various sources. Here's one of them. So this is Cambridge Isotope Lab. So here there are a list of these isotopes and also the catalog number. So in case you want to refer to this, so you can just order from here. So why do we need lock? So lock is actually required so that you can get the signal from the deuterium in the lock solvent, and then we can use that as our internal reference. So basically, we can every scan that you collect, that can be scaled back to your lock signal. This way, even if there are like small drifts in the magnetic field, we should be able to get very good data that we can superimpose, and then we can make it an additive process. And also the second thing could be that we don't, so this is a separate channel. So basically that will be separate from your signals that come from solvents. So basically, if it's deuterated, it's not going to show up in your proton spectrum. And then one of the few characteristics that you choose a certain solvent. So in case of biological molecules, you want to use water-based solvents or aqueous solvents. So you can use like H2O with 10% D2O, or you can use 100% D2O. But be careful, especially if you have like amides, hydrogen exchanges with the hydrogen in the water. And if you use 100% D2O, it can exchange to deuterium, which is not visible in proton spectrum. Okay, so you need to be very careful when you do these kind of choice of experiments. And also, I'm going to show you different ways where you can even use 100% D2O and get away with it. Okay, by using different kind of tubes. And for small molecule, all you should be focused on is like, is it soluble? Okay, so basically, try to get it into a very good solution. Usually, you can start with DMSO. DMSO kind of dissolves everything, so you can get deuterated DMSO, and you can start from there and then collect a bunch of NMR spectrum. But the problem with DMSO is if you want to ever go below its freezing point, like lower temperature, let's say 4 degrees Celsius, it's not possible. It could freeze and break inside the NMR spectrometer. So you want to use a different kind of solvent. It kind of is still in liquid state or at different temperatures. And of course, they should have deuterium in order to give you a good signal. So here are a few of these that you can buy, and you can store it in the lab and use this for every sample that you make. Be careful about D2O. If you buy it in large quantities, it can exchange with hydrogen, that is with water in air. So you'll get some contamination of water as well. So if you bought a bunch of like a liter of D2O, you're over, let's say, 4 years, is going to slowly build up hydrogen in it. And when you run the spectra, you will see the signals from hydrogen, which you don't want. So yeah, be careful when you do deal with deuterium, D2O. Okay, so in terms of NMR tubes, here I put the catalog number in the bottom. This is from a company called New Era. Kind of cheapest as well as kind of like good in quality. So this is my recommendation. Again, I'm going to give you catalog numbers of other vendors as well that you can use as a reference. Okay, so on the left side, what you see here is the 5 millimeter NMR tube. So basically, if your sample volume should be around 450 to 500 microliters, a lot of chemists they have a lot of samples, so they add everything in the NMR tube. Please don't do that. Just if you have more of your sample, just add 500 microliters. Don't fill it up all the way. That is not good practice, and I'll show you what's going to happen if you do that. Okay, and basically there are two different spinners that you can use. You can use these blue spinners that you are used to. They are 5 millimeter plastic spinners. So if you were to ever require high temperature or really low temperature, you can use these ceramic spinners. So one thing about using low temperature or high temperature NMR tubes is that get a good quality NMR tube. Okay, don't just buy the cheapest NMR tube if you want to do something at a different temperature that is like really hot or really cold temperature, because they can break, and that's not good. So invest in something that is good quality in order to go to the other things other than room temperature. So, if you have very little sample, that is the usual case for a lot of biological samples. You can use this tube on the right-hand side of this slide. So that's a 3 millimeter NMR tube. The catalog number is in the bottom. So the problem with this is we don't have enough of 3 millimeter spinners. So they are like a little bit smaller than 5 millimeter, and you need to use that. Or you can use these white inserts that you see over here. They're made by Norel. So you can buy it for your lab if you're routinely going to use this. Okay, so this way you need to you can still use a 5 millimeter spinner here that is in blue, and then put this insert, the white one, in there, and then put the 3 millimeter insert. So we have three inserts, one for 3 millimeter, 4 millimeter, as well as 1.7 millimeter in our next to our spectrometer, but we only have one of each. So if you have multiple samples, you need to probably order some of these inserts if you want to use this, or you probably need to take your sample out, put the next sample in, and so on and so forth. The other solution is like a hybrid between these two. So that is this catalog number in the bottom. So it's actually 3 millimeter at the bottom and 5 millimeter at the top. So basically, what this means is you can use this in a regular 5 millimeter spinner, and then you can get away by using 200 microliter of sample. So less sample doesn't always necessarily mean that you're going to get the same intensity of signal as 5 millimeter tube. So of course, because you're having less of your sample, your signal is going to be less as well. But some advantages, sometimes what happens is when you have way too much salt or something that kind of is highly conductive, so you want to you want to be as far away from the NMR coils as possible. That is why you would go to these 3 millimeter NMR tubes. So that is your standard NMR tubes. Then of course you can. My other recommendation for biological samples, as well as where you have very little of small molecules that you extract from various sources, use something called a Shigemi tube. So Shigemi tube has like an outer tube that is this thing over here, and then there's a plunger. Okay, so usually you can get away with somewhere around 250 microliter of your sample, and what happens is like this glass is a very special kind of glass, and you can buy these tubes matched to different solvents. So basically, if you had a biological sample, you'd use a D2O matched NMR tube, or if you have CDCl3 that you're using for your small molecule, you can use a CDCl3 and so on and so forth. So solvent matched NMR tubes. So advantage of using Shigemi is you can get away with smaller sample, as well as you can like seal them up. So kind of like yeah, it could be like preventing any kind of air coming in, and also because more of your sample is in the observable window. So basically, if you had 450 microliter of a sample, you concentrate it down to half and put it in here, and then you will probably get more than 2 times of signal to noise for this sample, just because more of the sample is in the observation window. So there are these portions of NMR tube that don't contribute to the signal that you observe. So basically, the Shigemi tube gives you that particular advantage. So the problem with Shigemi tubes are they're a little longer. So be very careful of not like that is if you're using something called a sample jet, which we don't have. So you might have issues. So you then stick to just regular NMR tubes in that case. And the other thing about Shigemi tube is they're expensive. So yeah, be careful, don't break these. So let's say you have a sample that you forgot to add your lock solvent. Okay, so something like you had a sample that doesn't have D2O, so you just had a water-based sample. So what you can do is you can get these inserts. So these inserts kind of go inside a regular NMR tube. So this can have a different kind of solvent, or if you had something like a standard, like a DSS or TSS that you use every time in your NMR spectrum, you can create one of these inserts, fill it up with your solvent as well as your DSS, and then use that every time. So you just put that insert in every sample that you collect. So that way you have an internal standard. So you can also use coaxial tubes. They're a little more expensive as well as little painful to use. So my recommendation is use these inner coaxial tubes that can go inside your regular NMR tubes. And sometimes people also have some like a standard, like a known concentration of something. So you can have that in this inner tube, or you can have some kind of like an acid or base or something that is very, very detrimental to your sample that you want to observe, but you don't want it to come in contact with, and you want to keep it separate, and that's what you can do. You can use that as a lock solvent. Okay. In fact, I have one of these right next to the 800 that has D2O with DSS. So in case you forgot to add D2O, you can just put in this insert and collect your NMR data. So shimming is going to be a little bit of problem, but yeah, we have other techniques that I'm going to show you that you can shim this very well. Okay, so talking about NMR tubes, there are like different kinds, there are different catalog numbers, different prices, different vendors. Okay, so what you should be looking for are the inner diameter, outer diameter, mostly the outer diameter, because that is your the spinner is what is going to hold this. So if you buy 5 millimeter NMR tubes, you have to use 5 millimeter spinners and stuff like that. So the other things that you need to be concerned about for an NMR tube that you buy is concentricity. That is how parallel the walls are. What is the tolerance of the inner diameter? Is it straight? Is it like bent and all that stuff, right? So basically, the cheaper ones that you buy, they have issues with one of these things, so that's why they're cheap. So the expensive ones that you buy are bend really well. So basically, they are like done, they are like picked out such that they don't have any issues with one of these parameters. Okay, so this is one of the vendors, Norel, and the catalog numbers on the left-hand side. The tolerances are listed here as well. So basically, the lower the tolerance it is, the better the NMR tube is. That also makes it more expensive. Okay, so you want this number to be very, very small. That is this tolerance, and you can buy either 7 or 8 inch tube, whichever you require. So you can get the high resolution one if you want to go to a higher spectrometer, and a low, like you can get the 300 or 400 when you want to go to a lower field NMR magnet. So same thing is true for Wilmot Glass. So they are another big NMR company, and their catalog number is here. They also have this economy tube. So as you can see, the economy tube has a much bigger tolerance number as compared to this. Okay, at least 2-3 times. So that's why they are cheaper as compared to your precision NMR tubes. Then New Era also has their set of NMR tubes. So if you ever had any kind of biological sample, you want to get this particular catalog number. And this is their economy tubes. They're like around like $2 to $3 an NMR tube. This is like $13 an NMR tube as of today. But anyway, so the tolerances here are excellent. It even beats any the other competitors. So if you want to purchase from New Era, this is the catalog number for this NMR tube. So I have given 3 different vendors and the catalog number, so you can order the right NMR tube for the spectrometer that you use. Okay, so now let's say your sample is in tube, right? So now what? So wipe the outside of the tube with a non-marring tissue. So make sure you use something like a Kim wipe so that you don't scratch it. Place the cap and seal it with parafilm. So most of the time, water can like evaporate. So that is a good practice to actually use that. If you have like broken tubes, discard it. Buy a new NMR tube. Don't cut your fingers. They are very sharp, especially the things that are broken in the top. So never dry your NMR tubes in a vacuum chamber at high temperatures. What happens is, so even though glass is a material that looks solid, it's not. So it eventually will, like, succumb to gravity, and that is kind of accelerated by high temperatures. So always use low temperature if you ever want to use a vacuum oven to dry your NMR tubes, or just keep it in your rack and use it the next day. That's an easy way to dry your NMR tubes. So this I've already mentioned. Don't use low quality NMR tubes, especially when you want to do low temperatures or high temperatures. They can break inside the spectrometer. Okay, and this is very important. I tell this to everyone who I train: label your sample, because if you can't find your sample, then you can't complain. Okay, so label your sample. Then anyone who picks out sample knows whose it is, and they can like store it in an appropriate place for you to find. Okay, so for labeling, again, this is a catalog number. If you ever want to buy this, or if you have tape in your lab, use that. Don't kind of like remove, put like a extension to your labels. Just use a tiny piece of like a label. So here, I usually recommend people to put their sample name, date, identifier. It depends on how small you can write on this tiny little space. Use a fine tip marker, and don't use a long sticky tape or a post-it on the top. Okay. So these are like, general recommendation. I'm not saying that this is what you guys do. I'm just like giving you resources that you can use to label your samples and identify it later. So in terms of solubility, you need your sample to be very well dissolved. It needs to be like clear, or if it has a color, then it needs to be very well dissolved, and you need to be kind of like seeing through it. Never ever vortex your protein samples. This is very relevant to protein samples that you prepare. But if you had a small molecule, I guess people do this. They kind of vortex it. So don't use that knowledge on something like protein because they kind of like form bubbles. So don't do that. The If you have like turbidity in your sample, that is not good. You're going to have a terrible NMR spectra. So you spin it down, remove your precipitate, and then collect your NMR spectra. So if you have precipitation, that is not good either. So sometimes these precipitates could trigger aggregation of things that are in solution as well. So if you see precipitation, I would take it out, spin it down, take out the precipitate, just take the suspension and look at it. And whatever is in the precipitate is gone. Okay, so that is not contributing to your your NMR signal. So that will show up in your denatured gel. Okay, but that doesn't mean that that's going to contribute because it's at the bottom of your NMR tube. Sometimes you could have like a phase separation. That's not good either. Okay, it needs to be very well suspended, just like in the first case. Okay, that could be concentration gradient. So you need to pipette it really well. Okay, you just can't get away with just adding things in the top and just running your NMR. So you need to take your sample out, do very good pipetting if you're doing titration, pipette it up and down a few times. Okay, and don't use too little sample. Too little sample is not good. Too much sample is not good. So if you have very little sample, you're going to have trouble shimming and loads of other problems. And finally, if you have bubbles in your sample, that's not good either. So don't be really quick when you put your sample in. Be gentle and pipette it very, very slowly. So, if you're really slow, you can avoid bubbles. And sometimes you can't avoid bubbles. That's totally fine too. Okay. So these are general recommendations. If you have any of these issues, go back, try to optimize your buffer conditions or your solvent to actually get good NMR data. Don't proceed if you have precipitation or turbidity and all that stuff. Okay. So when you take your sample, you put it in your spinner, only touch this portion of the spinner or probably the top portion of your NMR tube. Don't touch this bottom portion because that comes in contact with your probe. And over time, if the probe gets dirty, eventually you're going to get really bad NMR data because there's a lot of gunk on the probe. Okay, use this template that is right next to every spectrometer. So that gives you a guide of where your sample should be, and then basically make sure that your sample is centered in that line that is shown here. That is this line over here, as well as this rectangle covers most of your sample. Okay, and you have each rectangle for different NMR probes. So all our spectrometers have a 5 millimeter NMR probe. So you'd use that guide to actually make sure that that kind of covers your sample. So here again, I would stress if you have way too much sample, take a sample out. Okay, just make sure it's around 500 microliters. We're using a 5 millimeter NMR tube. Okay, and center your sample. Don't use what is shown in 4. It needs to be what is shown in 5. That is this guy. So it's kind of like centered, very well centered, and then take your NMR tube and put it in the sample transport, or a sample case in our case. Okay, so here again, I'm just reiterating all the things that I said. Okay, so what are the best practices for choosing appropriate instrumentation parameters? So basically, now that we have covered how to make good samples, now we will proceed to what things that you can change on the instrument. Okay, so here is my general recommendation for which spectrometer you want to use for what. So if you want your highest hydrogen sensitivity, you would choose the 800, the 600 a little less sensitive, and the 400 is least sensitive because it's a room temperature probe. And there's a Prodigy probe, there's a cryo probe on the 600. So in terms of carbon, the 600 gives you good enough spectra that you can start carbon on 600. Of course, the 800 is going to be the best signal to noise for carbon, and the Prodigy probe also gives you good carbon spectra, and the 400 is kind of okay with your carbon. You probably need to run really long NMR spectrum to actually get good carbon spectrum. Same thing is true for nitrogen. The nitrogen sensitivity is very similar for both 600 NMRs, and the 800 is the most sensitive. Okay, so but the advantage of using the broadband probe for the 600 over here that is in Mary C. Coleman Hall is that you can look at other nuclei as well, because the X nuclei could be anything on your periodic table that you're interested in. In this case, you can't use these two because there's an HCN probe that is currently installed on the high field magnets over here in chemistry building. Okay. Okay, and the other thing that you see here is automation. If that is something that you're interested in, use the sample case. And once you have the automation set up the first time, ask me on Minly. We can like set up something very specific to what you need, and then you can use that every time you come in. You can just select these are the 10 experiments I want to do for 10 samples. You can just copy paste, and that should be very very easy. Okay, so use the automation as you see fit. Okay, so in terms of experimental setup, so we do these steps manually at the 800, especially the people who don't use automation. So we will see a few issues that could happen and how you can solve it. Okay, so first is your temperature, then we can go to log, tune, shim, and 90-degree calibration. So let's look at the temperature first, right? So basically, the temperature that is shown in your NMR spectrometer is the temperature of the sensor that is in there. Okay, that is not your sample temperature. So what does that mean? That means that when the moment you put your sample in there, the sample doesn't magically go into the regulated temperature. Okay, so it requires a little bit of time. The amount of sample that is in there is a lot, and it has its own heat capacity, and it takes time to get to this particular temperature. So what you see over here is just the sensor temperature that's on the probe. And the other thing is that the sample is heated or cooled from the bottom. Okay, so this is what Bruker has inside your NMR probe. So what this means is that you want to wait. Okay, so in your automation, what we have done is like we have given it a time of like 2 minutes that it waits, or 5 minutes on one of the other spectrometer. So what it means is it puts a sample, waits for it to equilibrate, even if it's room temperature, kind of like tries to maintain the temperature. Okay, so basically do that. So if you are in a hurry, just go get a grab a coffee or something, come back and then start your NMR experiment after you put your sample in there. Wait a little bit, especially if the temperature is not room temperature. Okay, and make sure that there is adequate airflow, because if there's not enough airflow, so this is in the ED like in your VT control, you can see that there is this airflow that has been set by us. This is good enough for now, but if you have something that is kind of like really hot, some experiments that you want to run at like let's say 55 degrees Celsius, you want to make sure that this is kind of like at the correct airflow. You can increase it to make sure that it is in good equilibrium. Okay. The other thing that you want to look at is the second tab in the temperature control. So you just double click on that temperature at the bottom of your top spin, or you can type EDTE. You'll come to this window, go to the second tab, monitoring. You can check your sensor temperature as well as your NMR thermometer as well as your target temperature. And if it is a different temperature, it will go to equilibrium. So you want to wait till it equilibrates. Okay, usually 5 minutes. That is my recommendation. 2 minutes to 5 minutes. Okay, so sometimes you will have issues. Sometimes the temperature that you see does not match with the data that you collected, let's say 5 years ago. That could be because of various reasons. The age of the heater could be different. The cold air that is coming in could be at different temperature. So basically, we need to calibrate it. So this calibration is done yearly. Me and Midley do this. So basically, we would use D4 methanol. Methanol has two peaks, and this difference in peak is directly proportional to the temperature. So basically, with the separation of peaks, we can back calculate what the temperature is, and then we can do this calibration. So that is the correction. So that is why in like the previous slides, you would see that it says CORR 25. So that is what it means. It's corrected for 25 degrees Celsius. Even though the sensor, you see measured value, I guess it's not showing up there, but it shows that it's around 25.4 degrees Celsius. So even though the sensor reads 25.4, it's corrected to 25 degrees Celsius. Okay, so that is what this correction does. And also we use something called PID. P is your proportional, I is the integral, D is your differential. So we use this PID controller to do your, you know, continuous maintenance of your temperature. So if you're having issues with your sample that your signals are very broad, it could be that your temperature is not stable. You could be like changing temperature as you're collecting your spectra. So in that case, you would come and ask us, hey, what is going on? We can check if it is kind of like unstable, then we can come over here and tune it for you. So we use this PID controller to calibrate, do our self tune, and then use that to actually maintain the temperature of your sample in there. Okay. Sometimes you probably need to also adjust your chiller power. Okay. So this is on the 800 NMR. So you can set this BCO power to medium if you want to go to high temperatures, and you want to set this to max. So that is over here. You set this target power to max if you want to go to lower temperature than 10 degrees Celsius. So sometimes people forget to change it from one state to another. So if you want to run something at 30 and this is set to max, it's never going to reach 30. Okay. People have waited for hours and it said, hey, does it go to 30? This is what you need to do. Okay. So keep that in mind. So if it's not going to 30, your automation hasn't started. This is why. Okay. The next thing is lock. So Icon NMR does a great job at locking at different solvents. That is because Minley and I kind of like have a good like a lock table that it uses to find the lock signal. But you could have a lot of issues. Okay, so this is what happens if you don't have like you didn't select the correct kind of solvent when you collect your data. So let's say you had a sample that is kind of like locked to um, to deuterium in D2O, so this should be D2O. I'm sorry. But yeah, so if it's locked to D2O, then you're going to get a good spectrum, and the signal from water is going to be at 4.7 ppm. But you selected the wrong solvent. So basically, you selected DMSO. So the signal that you see in your H2O is referenced back from that, and then it is going to be at somewhere around 6.7 or something like that. And in that case, all your signals are shifted by that much. And if you didn't have enough correct sweep width, it could get cut off as well. So you need to be very careful when you kind of like choose a solvent, choose the correct solvent. Okay, that is what the slide is saying. Okay, or else you might have things moved around in your spectrum. So this is one of the cases I think Sam is in this audience. So he had like two different solvents. One of them was D6 DMSO as well as D2O. So basically, it's kind of in very similar concentration, and our spectrometer was either locking to D2O or locking to DMSO. So it was a big problem. So you probably need to like be very careful. So this is a like a deuterium spectrum that we collected. We know where our signals are. Okay, this is where D2O should be, this is where DMSO should be, and then use that to kind of like lock to one of them, and then use that as a reference to lock everything else. Okay, so be very careful. If you have more than one lock solvent, you're going to have trouble. So here is one of those cases. Okay, the other thing that I would recommend that Icon NMR does automatically is it does auto gain as well as it does phasing automatically for you. And this phasing is also automatic on when you do it manually as well. If you go to Edlock, we kind of have it enabled. But if you are ever use a spectrometer, it's not phasing correctly. So this is the phase of the lock solvent. Okay, so if it's not phasing correctly, you can go to the EDLOCK. You can type that and go to this window and then select, make sure that it's selected with auto phasing. Okay, again, because we have correct values in here, this phasing is correct. Okay, if you're having issues, come talk to us. We'll try to see if we need to adjust this based on the different issues that you're having in your locking procedure. And if you were to ever use a BSMS disk that's on this, so here is an example where the phase is wrong. You see the green peak is much lower than the red peak over here. So basically, you want to make sure the phasing is correct. So you can go to the BSMS thing and click on this auto phase, the first button on the left, and it will phase it for you. Again, you can do an auto gain as well after you lock. Okay, so these are the different things that you can do if you're having trouble locking. Icon also has a way where you can like do a manual locking as well. We haven't enabled it for anyone, but if you're interested, if you're having trouble every time you're locking into things, that is, it's locking into a wrong solvent or wrong section of the solvent, let us know. We'll try to figure this out for you. Okay. Um, the other thing is always tune your sample. So if your tune is off, your 90-degree pulse is going to be longer. So which would mean that you're pulsing much more. You're putting a lot more radio frequency pulses. So spend that little time and tune it. Again, Icon NMR does this automatically for you. The new algorithm for tuning and matching is pretty good. It kind of is very robust. Even if you have something that is kind of very far off, it's able to find that and kind of like sorry, tune and match to the correct nuclei. So you want to do this for every nuclei that you're interested in. So if you're going to run C13 spectra, make sure that you lock, tune, and match for the C13 channel as well. Okay. For shimming, there are different things that you can do in a more advanced way to do this. Is use something called top shim GUI. I think what you guys usually do is top shim, and then you can add some parameters on top of it. So in the GUI interface, you have this 3D shimming. You want to do this especially when you have some kind of issues with your shimming, and this is only applicable if you have a 90% water, 10% G2O sample. In that case, you want to do the 3D shim. What it does is kind of like maps the whole three-dimensional space of your NMR sample and kind of make sure that it's kind of like homogeneous magnetic field when you do these kind of perturbations. You can obviously tune the different parameters after or before shimming, and also you can put in additional parameters. We'll go over what you need, what are the things you can do. So most advanced parameters are, if you use a Shigemi tube, you can tune for Shigemi. If you have way too much sample, you can or you're using really high temperatures, you can have convection. You can do something called convection compensation. Or if you have small volumes, you can decrease the number of tuning steps that you need to do, so it only tunes for the small portion of the sample that you have in there, or else it's going to fail. It's going to say, hey, I can't shim anymore. Okay, so here is where you put in, so you check mark the parameters and put in Shigemi. So this is used for Shigemi tubes, and this can be combined with other parameters. Okay, so if you have like a hot sample or something that is really different in temperature, the top of the sample is different from the bottom, so you'll have some kind of like convection going on in your sample, or if you have way too much sample, the things could be moving around. Okay, so in that case, it's never going to shim, it's going to error out. In that case, you can come in, manually put in something called conf comp, so it kind of has an algorithm, kind of figures out what needs to be done such that the magnetization is uniform or homogeneous when you do your experiments. So this is also useful when you have low viscosity solvents as well. So if you have very little sample, you can use odd max equal to 3 in here in parameters. So that uses Z1 to Z3, and make sure that this is kind of like in your on your line, very well centered. But this is not my recommendation. So this is kind of like trying to give you a tool to kind of shim your sample, even if you have very little of your sample, but that could be, the shape could be very, very weird. And this is just to get away with getting you some kind of data, okay, and some kind of shimming that can be done. So here are, you can use odd max equal to 8 as well, so you can use Z1 to Z8 depending on the probes or how many coils that are inside the probe. Okay, so those are three different things that you can do to shim. That is a little more advanced than what you usually do. And then the last step in our calibration is our 90-degree pulses. So basically, in 90-degree pulses, you can do a manual calibration, but by default, everyone here uses, I guess, pulse cal. Even Icon uses pulse cal. So what it does is kind of like tries to optimize to figure out what is your maximum signal that comes out of your experiment. But if you were to ever do a manual calibration, this is what it'll look like. So it'll slowly rise up, go to like a 0 point, then go down and go back to the 0 point. So some people do this point, there is a 180-degree calibration, or what I recommend people to do is a 360-degree calibration. So you'll get a negative signal, and that negative signal becomes a positive signal. So you can find the null point, which will be somewhere around here, which is in this case somewhere around 42 or 41 microsecond. Okay. So once you know what your 360 degree is, your 90 degree is one fourth of that. Okay. So usually these algorithms are not good in finding the maximum, but it's very good at finding the null point. Okay. So you find the 360 divided by 4, and that is how you do your 90-degree calibration. Okay. So probably in Varian, you're also using the automated single button click that does pretty much the same thing. Okay. So now that we are done with this section, so next is how to get good acquisition parameters that you can use for your NMR spectrum. So general NMR experiment is you have a D1 period. So that is the period that you wait for equilibrium to go back to Z. Then your magnetization is a Z at the beginning of your experiment. And then you do your experiment wherein you kind of like do different things. And then eventually you put it on this XY plane. And that is where your receiver is. And then you do your acquisition. Okay. So this is what it's going to look like. So this actually not a continuous thing that you measure. It's a digital signal, so it's going to be like recorded as these points, and then you can like separate out X and Y, and then you can do your Fourier transformation, and this is your FID, and then you can convert this time domain data to frequency domain, and that is your NMR spectrum, right? Okay, so basically, what does this mean? So basically, you have these three different periods, right? Equilibration, perturbation, and your acquisition. So basically, you're spending like 2 seconds usually for equilibration. 0.05 seconds is how long it takes to run your actual experiment, and somewhere around zero point 0.1 seconds to do your acquisition. So which means that you're spending 93% of your time of your NMR, the experiment in your D1. Okay. That's a lot of money, and you're not doing anything over here. That is, you're spending a way too much time on your D1 as compared to the rest of your, section of your NMR experiment. So basically, that means that easy solution is let's just use a small D1, right? So if you use small D1, you will have other problems. So one of those problems is a lot of your quaternary carbons will go missing. So basically, if you now increase this by 5 times, it comes back. The only difference between these two is exactly same solvent, same sample. Only difference is that this is way too short. This is around 0.1 seconds. This is like 5 seconds. Okay, so basically that is why you're actually seeing these peaks. So if you ever have quaternary carbon, you're running carbon spectrum, don't use D1 equal to 1 second. Use something bigger. Use something like 5 seconds as your D1. This is one of the parameters I recommend you to change. Okay. So if you have short D1, you could also have a lot of artifacts that show up in a two-dimensional spectrum over here. So make sure that you don't kind of like take shortcuts to save time, but then you get all these artifacts and you're like, why am I seeing all these things that is not visible when I had D1 equal to 1? Okay. So the other thing is your acquisition time. So most of your signal is in this example over here is over here, and the rest of it is noise. So if you kind of go in this direction, add more points here, you're kind of increasing your resolution, but you're also increasing your noise. And if you kind of make it too short, you're kind of truncating it as well. So kind of like a double-edged sword, right? So you need to use good acquisition parameters to get good NMR spectra. So if you have a very short acquisition time, you'll see these artifacts that show up like this. So you'll also have a lot of resolution loss as well. And this is called sync wiggles. So you'll have these wiggles that go all the way across your NMR spectrum. That could be because when you have very little acquisition time, or you have not collected enough of your data. So all this data that is recorded over here is missing. So you just use very short time over here, you're going to have a spectrum like this. So if you see something like this, please go and increase your acquisition time. Okay, so this is one of those recommendations for you. The other thing is don't go overboard. In this case, this is an acquisition time of like 14 seconds. Okay, it's like 40 seconds of doing nothing. You're just waiting for your equilibration to come back. And here the acquisition time is 5 seconds. You're not gaining any excess, um, sensitivity by using larger acquisition time. So that's why this is a double-edged sword. So don't use too small a value. Don't use too big a value. So it's kind of like uh, it's just painful when you have to like adjust this. But if you have a good acquisition time, you can get a very good spectra for the resolution that you collected. So longer acquisition time will lead to lower signal to noise, and this can be fixed by TD effective. So basically, what this means is you can just collect more of this data and then cut it off, and then just do your Fourier transformation of this particular region. You can do zero filling, linear prediction, and get good data based on your TD effective. Okay, so that is one of those things that you can set and um, in your processing parameters, as well as you can do this in MNOVA as well. Okay, so the other thing that you can do is NOAA experiments. So the NOAA experiments is NMR by ordered acquisition using proton detection. In this case, you just have one D1, and then you just combine these experiments one after another, and then you start over. So which means that you're not doing one D1, then your experiment, then D1 and second. And so instead of that, you're just using one D1 and you're running all your experiments. Okay. So in this case, this is one example where you have HMQC, HSQC, COSY, NOSY, and there's only one D1 over here. Here are two different examples. Here, the example on the left, it only took, I guess, 21 minutes to collect this. And within that same time, you're collecting one HMQC, HSQC, COSY, and NOSY. This is NOAA 5 super sequence that you can use as well. In this case, you get HMQC, HSQC, HMBC, COSY, and NOSY. So this is kind of like advantageous. So basically, within the time span of one experiment, you have collected 4 when you run the NOAA 4, and when you use this is the NOAA 5. The only disadvantage of NOAA that I have seen is that you probably have to use the same sweep widths. So basically, all of them, you see, they're kind of like same sweep width. So that means that you kind of have to make sure that the sweep widths are correct, and it kind of is not all that difficult to do, and you just run this just like a regular NMR experiment. You just load these experiments, say run, and yeah, you do your standard calibration, and you can just hit run. So they're already implemented on most of our spectrometers because these can only run on a newer Neo console, and everything that we have is a Neo console. That is Bruker is all Neo consoles. So the other thing is your receiver gain. This is also done automatically by Icon if you use Icon NMR. So if you have too high of a receiver gain, you would get this kind of error. Hey, you're receiving an overflow. It's called ADC overflow, and you're missing a lot of signal over here because your amplifier is turned way too high. And if RG is too low, you're not getting enough signal. It's kind of like very, very weak. So my recommendation, always do RGA if you are manually doing this, or adjust your RG depending on the quantity of sample that you have. So this is the exactly same sample for different RG values. So because this person did not set up the correct RG value, you will see a very small signal to noise as compared to where the RG is set to the correct value, which is the highest value on all our spectrometers 101, wherein it's kind of like giving us a good NMR spectrum for the exact same sample. So setting up the RG is very, very important for getting good NMR spectrum. So a lot of times you can have like water in biological samples. So this is one of those examples where you can use water suppression. So here you see this is the exact same sample with water in it with 4 scans. Most of the signal is water. These are these tiny, tiny, tiny signals. But once you do this particular experiment where you suppress the water, which is at around 4.7 ppm, which is this tiny little peak that you see here. So it's very well suppressed. Just because that is suppressed, now you have signals coming from everything else around it, and then you can analyze this. Again, this is just an example for water. You can do these kind of solvent suppression for different kind of solvents. So in this case, you would calibrate the O1P, you would calibrate the 90-degree pulse, and if you use the pre-saturation, you need to calibrate the pre-saturation power as well. So those are a few things that you need to do. Also, my recommendation is use appropriate sweep width. Okay, so sometimes you don't have any signal at around this region, and you have a very big sweep width, and so most of it is useless over here. So in that case, you would use this sweep width. But when you set the sweep width, you would set something called an O1P, which is the center of your sweep width. And most of the times, when you're using solvent suppression, that needs to be on top of your solvent. In that case, this will be on top of somewhere around here or here, 4.7 ppm. If this was a water-based sample, in that case, you need to use much bigger sweep width, and you'll have useless areas, but then you have no way out. But if this is the case where you are not bound by like putting it on the solvent because there are no hydrogens from the solvent because it's a DMSO sample. So basically, you can then use the correct sweep width where the correct sweep width that you're interested in. Okay, so sometimes people use small sweep widths. That is, they just use sweep width only up to 10 ppm, but the signal shows up at like 11 ppm, right? In that case, you want to make sure the sweep width is big enough. Okay, and you will come to me like, oh, why did it not collect the correct sweep width? And that is because it's not set correctly. So the icon NMR reads these values. You can set these values, and you can it'll respect the value that you put it in there. Okay. So the last few slides, the last section is the efficient data collection strategies. So if you're given a chance between your regular HSQC-based experiment and a TROSY, use a TROSY experiment. So TROSY is your transverse relaxation optimized spectroscopy. So it selects one of these components in your HSQC. So if you run an HSQC with decoupling in both proton and your nitrogen dimension, you're going to get 4 peaks, and your TROSY selects this peak. So if you have the decoupling turned on, it's going to be one of these in your HSQC spectrum. But in your TROSY, you just select this peak, you cancel out all these signals from here. It's going to be shifted by half JNH, but your signal is going to be much more sharper. It's going to have much higher signal to noise. So you can get away with less sample because you have much more signal using the TROSY principle as compared to the HSQC. The other thing that you can do for protein-based NMR is band selective excitation or best experiments. In best experiments, you can just excite this region, that is the amide region, and then you can collect the spectrum. You can use biotop to set this, where you set the center as well as your sweep width to excite only that region, and you don't care about this region. So that way it kind of like speeds up. You don't have to worry about your relaxation of water. You're only exciting this region, and that is what is going to show up in your receiver. The other thing that you can do is non-uniform sampling. As you know, most of the NMR data in higher dimensional NMR is very sparse. So these is how much that is your distribution of signal for ubiquitin from one of our previous workshops. So you can like use sparse sampling, somewhere around 25% sampling, and you can get away with 25% of the time of collecting this whole 3D experiment. So something that took days is now going to be collected in like an hour or a few hours, and then you can use mathematics to figure out where the rest of the signals should be, and you can do your Fourier transformation, and you will get a very good reconstruction of your data as long as you have high enough signal and your data is sparse. Okay? You can also manually set these values in your topspin by setting this NUS amount by amount of sparsity. So you can start with 40%, 50%, and you can go lower as you have higher concentrations. And you need to select the FN type as non-uniform sampling. And you can also set these up using the biotop interface if you are using biological samples. Again, NUS can be used even for small molecule. You can because this is an advantage for small molecule people as well, because you guys have way too much of your sample. You have very concentrated sample. So you don't have to wait long to collect the whole spectrum. You can get away by doing non-uniform sampling, and you can save a lot of time. Your HSQC could be like a 2-minute HSQC as compared to 40-minute HSQC. You can even do like a 2 to 3% sampling as well. So the last few slides are about choosing the right experiments. Here are just my recommendations, and this is a very broad recommendation. Uh, and we have other experiments as well along with these, so you can like choose the correct experiment. For COSY, if you're given a choice, run DQF COSY because you also get coupling constant. You can do linear prediction zero filling, and you can get more data than your regular COSY that you've been used to or trained to do. Okay. For Toxi experiment, where you see your in like your bound carbons. So basically, you can either run MLab as well as DIPSI. So choose whichever you're familiar with. My recommendation is use MLab, and then we have various variants of these experiments to run your particular sample. For NOSI, where you get information about how close hydrogens are to each other, wherein the distance is r to the power 6 proportional to the NOSI signal that you observe. So my recommendation is to run this excitation sculpting experiment, wherein there are no secondary areas that get wiped out. Only the region that you're interested in, that is the solvent, in this case a water-based solvent, is wiped out, and then you get signals from everywhere else in your spectrum. In this case, this person had other things here. You see those signals are still present. Okay, so my recommendation is use the excitation sculpting if you have some kind of solvent that you want to suppress. Okay, here is a table of different experiments that you can start with. For proton carbon experiments, you can run this particular HSQC variant. For HMQC, you can run this variant. For HMBC, you can run these variants. Talk to me or Minley. We have already a set of starting experiments that you can start with for each one of these, and then we can like optimize it for different cases. If you're not happy with the signals that you see from here, we have other variants that you can use. For proton nitrogen, you can use HSQC and TROSY. We also have best version, that is the B underscore versions of the same thing. And if you're in a hurry, you want to do a quick like so fast HMQC, you can run this. Talk to me how to set this up. I'm happy to help you with that. And if you're running a carbon nitrogen CON experiment, use this parameter set. Again, these are your starting parameters. You can combine it with non-uniform sampling and collect the same kind of data. So this kind of summary of where you can start, and then you can end up with a different pulse program. So get in touch with us if you have very specific experiments you want to run, but these are the good starting points, and anywhere you go, you can use this as your reference as to where you want to start with. So that's it. So that is all I have. So if you have any questions, let me know. We're happy to answer.